In an earlier video, I've written down a form for the cost function for logistic regression. In this optional video, I want to give you a quick justification for why we like to use that cost function for logistic regression. To quickly recap, in logistic regression, we have that the prediction y hat is sigmoid of W transpose X plus B, where sigmoid is this familiar function. And we said that we want to interpret y hat as the probability that y is equal to 1 given x. So we want our algorithm to output y hat as the chance that y is equal to 1 for a given set of input features x. So another way to say this is that if y is equal to 1, then the chance of y given x is equal to y hat. And conversely, if y is equal to 0, then the chance that y was 0 was 1 minus y hat, right? So if y hat was the chance that y is equal to 1, then 1 minus y hat is the chance that y is equal to 0. So let me take these last two equations and just copy them to the next slide. So what I'm going to do is take these two equations, which basically define p of y given x, for the two cases of y equals 0 or y equals 1. And I'm going to take these two equations and summarize them into a single equation. And just to point out, y has to be either 0 or 1 because we're in binary classification, so y equals 0 or 1 are the only two possible cases, right? But so I'm going to take these two equations and summarize them as follows. Let me just write out what it looks like, then we'll explain why it looks like that. It's 1 minus y hat to the power of 1 minus y. So it turns out this one line summarizes the two equations on top. Let me explain why. So in the first case, suppose y is equal to 1, right? So if y is equal to 1, then this term ends up being y hat, because that's y hat to the power of 1. This term ends up being 1 minus y hat to the power of 1 minus 1, so that's the power of 0. But anything to the power of 0 is equal to 1, so that goes away. And so this equation just says p of y given x equals y hat when y is equal to 1. So, that's exactly what we wanted. Now, how about the second case? What if y equals 0? If y is equal to 0, then this equation above is p of y given x equals y hat to the 0, but anything to the power of 0 is equal to 1, so that's just equal to 1 times 1 minus y hat to the power of 1 minus y. So 1 minus y is 1 minus 0, so this is just 1. And so this is equal to 1 times 1 minus y hat, which is just equal to 1 minus y hat. And so here we have that if y equals 0, p of y given x is equal to 1 minus y hat, which is exactly what we wanted above. So what we've just shown is that this equation is a correct definition for p of y given x. Now, finally, because the log function is a strictly monotonically increasing function, maximizing log of p of y given x should give you a similar result as optimizing p of y given x. And if you compute log of p of y given x, that's equal to log of y hat to the power of y, 1 minus y hat to the power of 1 minus y. And so that simplifies to y log y hat plus 1 minus y times log 1 minus y hat, right? And so this is actually negative of the loss function that we had defined previously. And there's a negative sign there because usually if you're training a learning algorithm, you want to make probabilities large, whereas in logistic regression, we're expressing this, we want to minimize the loss function. So minimizing the loss corresponds to maximizing the log of the probability. So this is what the loss function on a single example looks like. How about the cost function, the overall cost function on the entire training set on m examples? Let's figure that out. So the probability of all the labels in the training set right? I'm writing this out a little bit informally, is if you assume that the training examples are drawn independently or drawn IID, identically independently distributed, then the probability of the examples is the product of probabilities. So the product from I equals 1 through m of P of yi given xi. And so if you want to carry out maximum likelihood estimation, right, then you want to find the parameters that maximizes the chance of your observations in the training set. But maximizing this is the same as maximizing the log. So I'm just put logs on both sides. So log of the probability of the labels in the training set is equal to log of a product is the sum of a log. So that's sum from y equals 1 through m of log p of yi given xi. And we had previously figured out on the previous slide that this is negative L of y hat I, yi. And so in statistics, there's a principle called the principle of maximum likelihood estimation, which just means to choose the parameters that maximizes this thing, or in other words, that maximizes, this thing, right? Negative sum from I equals 1 through m, L of y hat I, yi. And I just moved the negative sign outside the summation. So this justifies the cost we had for logistic regression, which was J of WB of this. And because we now want to minimize the cost, instead of maximize the likelihood, we've gotten rid of the minus sign. And then finally, for convenience, or to make sure that our quantities are better scaled, we just add a 1 over m extra scaling factor there. But so to summarize, by minimizing this cost function J of WB, we're really carrying out maximum likelihood estimation with the logistic regression model under the assumption that our training examples were IID, or identically and independently distributed. So thank you for watching this video, even though this is optional. I hope this gives you a sense of why we use the cost function we do for logistic regression. And with that, I hope you go on to the exercises, the problem exercise and the quiz questions for this week. Best of luck with both the quizzes and the problem exercise.